we continue our discussion on similarity transformations and how similarity transformations can help us solve non-autonomous equations. So, our general nth order non-autonomous system was given by equation of this form dx by dt is equal to Ax plus Bu, and then we also saw that we could have similar matrices, where similar matrices were defined as the matrices which have same eigen values, and the eigenvectors were related by this, that if x is the eigenvector of A, then for B P inverse A would be the eigenvector, and the eigenvalues for the two cases would be the same. The matrices A and B were called similar matrices. Then we also saw that if the matrices if a matrix has n linearly independent eigenvectors, then the matrix is diagonalizable. So, all you need to do is you need to do the operation P inverse A P, and this would give you a matrix lambda, capital lambda, and for this to happen what you need to do is you need to pose P as the one which has been formed by the augmentation of the linearly independent n eigen vectors, right. So, now we can in fact use this concept for solution of non-autonomous equations. Let us see how we can do that. So, we have equation, general equation, which is of the form d x under bar by dt is equal to A double under bar x single under bar plus B double under bar u single under bar. Let us remind ourselves quickly of the dimensions. X under bar was of the dimension n cross 1, A under bar was of the dimension n cross n, and x was of the dimension n cross 1. So, therefore, overall the dimension would be n cross 1. Similarly, B was of the dimension n cross m, and u was of the dimension m cross 1. So, overall the dimensions were n cross 1. Fine. So, we saw that mathematical compatibility exists, and therefore, we can, for the sake of mathematical ease, replace this entire operation of B multiplied by u will give me a vector, and let me call that vector as G. I will simply call that vector G, and to emphasize that G is a function of time, I will write this as G of t. Fine. So, let me rewrite my equation as dx single under bar by dt is equal to A double under bar x plus G under bar t. This is my nth order non-autonomous dynamical equation which I am trying to solve. Let us see how I can make use of similarity transformation to solve this problem. So, let me do a trick and multiply both the sides by P inverse. So, d by dt of P inverse x single under bar is equal to P inverse A x plus P inverse G. Okay. I will do one more trick here. I will multiply the second term by two quantities P inverse x is equal to P inverse A, P inverse P multiplied by x plus P inverse G of t. Let us see what did I do. I inserted an identity matrix in between, and I know that multiplication of identity matrix does not change the system, but how did I bring that identity matrix? I brought that identity matrix by multiplication of P inverse with P. So, P inverse multiplied by P is an identity matrix. So, this is what I did, and then instead of P inverse P, I will need to do this thing P inverse. So, a small correction here, I will make P inverse, okay. And then I will draw some brackets. You will quickly see why did I change P inverse P to P inverse, because when I see this, now I have the equation which is in a little elegant form. So, if P is made from augmented eigen vectors of A, this is what we learned in the previous lecture, that if P is made from augmented eigenvectors of A, then I know that P inverse A P is a diagonal matrix capital lambda. We learned this in the previous lecture. So, now I do this, this is 2, this is 1, then let P inverse x. So, P inverse is a matrix, x is a vector. So, this will result in a vector, and let me call that vector as y under bar, and also P inverse is a matrix, G of t is a vector. So, this will give me another vector, and let me call that vector as B under bar t. Okay. So, now I will substitute equations 2 and 3 in equation 1 to get this d by dt of y bar is equal to lambda the matrix multiplied by y under bar the vector plus b under bar t. I have now gotten a dynamical equation which is dy by dt is equal to lambda y plus b of t, and let us compare it with equation number say 0. So, instead of dx by dt, I have dy by dt. Instead of the matrix A, I have the matrix lambda, and instead of the vector g of t which came from the input vector, I have another vector b of t. I know the relationships between them. So, here instead of x I have y. What is the relationship between x and y? Well, I have this. So, if I know one of these quantities, I can know the other quantity. I have A and I have lambda. A is known to me and lambda is also known as a diagonal matrix. And G and T, what is the relationship between G and T? Again, I know the relationship. So, if one is known, the other one is also known. But what is the advantage of doing these intermediate steps so as to reach equation 4? The key difference between equation 0 and equation 4 is the appearance of this diagonal matrix, which would be a key advantage during the subsequent steps. So, let us see how do I solve this equation. So, I somehow have made up my mind that I do not want to solve equation 0 directly, it is going to be a little tedious. What I am going to do is I am going to convert it to equation number 4, and now I am going to solve it, and I expect that there would be certain advantages. Let us see how to handle equation number 4. So, the equation is dy by dt is equal to lambda y plus bt. So, we have the equation as dy under bar by dt is equal to lambda y plus b of t, b as under bar. So, before we solve this equation, let us write an analogous equation in one variable, and that analogous equation would be dy by dt is equal to lambda y plus b, okay, b of t. So, what have we done here? We have converted the vector y to simply the dependent variable y. We have converted the matrix lambda to simply a scalar lambda, and also we have converted the vector b of t as a simple function b of t. So, how would we solve the equation on the right hand side? We can solve using the method of integrating factor, and for that let me do one rearrangement. Let me write it as dy by dt minus lambda y is equal to b of t. Fine. So, if this is the equation, then the integrating factor can be identified very easily as e to the power minus lambda t. So, I will multiply e to the power minus lambda t on both the sides, e to the power minus lambda t dy by dt minus lambda e to the power minus lambda t y is equal to e to the power minus lambda t b of t. Okay. From where I can write the left hand side as d by dt of y e to the power minus lambda t is equal to e to the power minus lambda t b of t. So, this makes it d of y e to the power minus lambda t is equal to, so it has to be a t here, e to the power minus lambda t b of t dt, and then I can integrate it on both the sides, following which I will get y e to the power minus lambda t is equal to integral e to the power minus lambda t b of t dt plus an integration constant c. So, I can write the final expression for y as e to the power lambda t integral e to the power minus lambda t b of t dt plus e to the power lambda t times the integration constant c. So, when I have a simple first order linear ODE in one variable given by dy by dt is equal to lambda y plus b of t, then I can adopt a simple integrating factor method to get the final expression for y. Now, can I do analogous steps for the solutions for the equation given on the left hand side? So, let us see, let me write this as dy under bar by dt minus lambda. So, there has to be an under bar here, lambda y under bar is equal to b under bar t. Okay. So, you can see a correspondence between the steps which are given on the right hand side and the steps which are given on the left hand side. So, if somehow the steps which are given on the right hand side could be followed for the system which is given on the left hand side, then let me repeat, if somehow I can do whatever I did for the right hand side also to the left hand side, then my integrating factor would be for the left hand side e to the power minus lambda the matrix t dy by dt minus lambda the matrix e to the power minus lambda t y under bar is equal to e to the power minus lambda the matrix times t b the vector t, right. In this particular step, I have taken the exponential of a matrix multiplied by t. That may sound to be a little strange, but we will come to that point a little later. At this point of time, let us try to focus on establishing a correspondence between the two sides and get an appreciable expression. So, I can write this as d by dt of y under bar e to the power minus lambda t is equal to e to the power minus lambda t b under bar t. Okay. From where I can write d of y under bar e to the power minus lambda t is equal to e to the power minus lambda t b under bar t. Finally, y e to the power minus lambda t is equal to integral e to the power minus lambda t b under bar t plus. On the right hand side, I wrote a constant. You will need to see whether I can really write a constant here or something else. What kind of a quantity would that be? Okay. At this point of time, I would write here a constant vector. Why? We will see. C on the right hand side would come from the initial conditions, but on the left hand side you have a vector. So, you would have a constant initial condition vector, and therefore, you will have to write C under bar. Okay. And then finally, what you will do is, the way you took e to the power lambda t on the right hand side, for the right hand side you will write y, there has to be a under bar. I will write here e to the power minus lambda t inverse integral e to the power minus lambda t. Okay, there has to be a dt here, there has to be a dt here. Okay, b t dt uh, plus e to the power minus lambda t inverse times the initial vector constant. Okay. So, now why did I write e to the power minus lambda t inverse rather than simply putting it in the denominator? For that you must know what kind of quantity is this. Okay. In fact, all of these operations which I have now shown for the left hand side to give you the explicit expression for the vector y are not very difficult, except that I will now need to raise the exponential with the matrix times multiply times t. Okay. And if I can get hold of this particular quantity, we can actually find out the entire solution. So, let us then look into how we can actually get the exponential of the matrix. So, let us see how do you get this. So, the problem is getting e to the power minus lambda times t. This is the problem. So, can I exponentiate a matrix? This is the simple problem, right. So, I have the definition of e to the power x as 1 plus x square plus x plus x squared by 2 factorial up to infinity, right. So, if this be the case, then what I can do is I can do this e to the power now minus lambda t would be equal to, instead of 1, since you have the operations with a matrix, this will become an identity corresponding identity matrix plus x. X is simply the one which you see here. So, this will become minus lambda times t plus 1 upon 2 factorial minus lambda times t whole squared and so on. Fine. So, now the question is what would be the final functional form of this. Okay. So, this will become an identity matrix. So, this would be 1 0 0 and so on, 0 1 0 and so on, 0 0 0 1. This is the identity matrix. Now, the question is what is this? So, what is this matrix equal to? Okay. So, since I have lambda as a diagonal matrix, lambda 1 0 0 0 lambda 2 0 0 0 0 lambda n, what will happen? Lambda times t will simply be lambda 1 t 0 0 0 lambda 2 t 0 0 lambda n t. This will become the matrix. So, I will have plus lambda 1 lambda 1 t 0 0 0 lambda 2 t 0 up to lambda n t, right. Now, what would be lambda t squared? What would be lambda t squared, because you need this here, right. So, lambda t squared would be the square of this, and that is where the importance of diagonalization comes. Because this is a diagonal matrix, in fact you need to square this. Every element will simply become square root of it. Had it not been a squared matrix, it would not have been easy. So, what you would do is you would do lambda 2 lambda 1 t squared 0 0 lambda 2 t squared 0 0 lambda n t squared, and so on up to infinity. Okay. Every quantity divided by 2 factorial, because you have a 2 factorial here, and then you will keep on adding them. So, finally, what you will get, e to the power lambda t would be what? 1 plus lambda 1, in fact minus lambda 1 plus lambda 2 squared by 2 factorial plus lambda 1 squared by 2 factorial, and so on 0 0 up to 0, then 0 1 minus lambda 2 plus lambda 2 squared by 2 factorial 0 0 and so on, and here lambda 1 minus lambda n plus lambda n squared by 2 factorial and so on. But what are these individual terms? These individual terms are nothing but e to the power minus okay, and everything will be multiplied by t. We forgot t here, t squared, t squared, t squared. So, this is nothing but e to the power minus lambda t, right. Each term in that component of the matrix in fact is the expansion of exponential. So, therefore, e to the power minus lambda t is what? E to the power minus lambda 1 t, this is e to the power minus lambda 1 t, 0 0 0 0 e to the power minus lambda 2 t, 0 0 0 0 0 e to the power minus lambda n t. And then what you see is that the only problem which you had in otherwise solving compatible equations and doing integral, by the way, integral of a matrix times say dt, okay, is nothing but a dt, b dt, c dt, c dt and so on. Okay. So, the integration is never the problem. Integration of the matrix is simply the integration of all its individual elements. The problem was the exponentiation, and what we saw is that you can in fact exponentiate it using the method which we just now developed. The method was nothing but using a series expansion of the exponential function. So, e to the power x is 1 plus x squared by 2 factorial plus x cube by 3 factorial and so on. And therefore, what we did was we wrote this in an analogous manner, that e to the power matrix times t is equal to identity matrix plus the matrix times t plus square of the matrix t times t squared by factorial 2 and so on. What came to our advantage was that by doing diagonalization, the matrix multiplication and taking the power taking nth power of a matrix became very easy. And then since the individual since the exponentiation is in fact a process of taking infinite summation of infinite number of terms, you again had to do a summation of individual components. And then what did you see was that since the matrix was diagonal, all the off diagonal elements were 0, you were left with only the diagonal elements, and the diagonal elements themselves were nothing but the series expansion of exponential raised to the power lambda I times t. And therefore, we came up with a method so that you could raise a matrix to the power of e. The subsequent steps are not very difficult, as you did in case of single variable. You can do simple manipulation in case of matrices as well. The only trick was to do exponentiation. So, now what we will do is we will in fact use these concepts to study one of the physical systems. In the previous lecture, we saw that we had in the previous week, in fact, we saw the dynamics of a spring, where you had undamped and damped systems, but they were autonomous systems. Now, how to make the systems non-autonomous in case of a spring mass system, and how would the dynamics vary if you have a non-autonomous system? These are the concepts that we will take in the next 2 lectures. Thank you.